Let us move to our second asymptotic notation, which is big O, also called asymptotic upper bound. Here is the definition. Let Fn and Gn be two non-negative functions of non-negative arguments. So same like we did for theta, the Fn and Gn must be positive functions, and we're only concerned with the positive values of n. Remember, of course, this n is really the input size. Input size is usually positive, not negative. Therefore, that is why we are concentrating only on this side of the line, the positive side. We don't have to consider the negative, because input size for an algorithm is never really going to be negative. Remember, input is data, so how can you have a negative data? So this is the definition for big O. Say Fn is big O of Gn if we can find a constant C greater than 0 and n naught greater or equal to 0, such that Fn is always less than C times Gn for all n greater than n naught. So if you notice here, we only need to find two constants, the C and the n naught, unlike what we did for the theta. Because actually here, the big O is concerned only about the upper bound. It doesn't care about the lower bound. Alright? Unlike theta that cares about both. This is why the theta actually is called a tight bound. It is tight both from the top and the bottom. But here in big O, we are only concerned about the upper bound. Therefore, we only need to find one constant C, which is strictly positive, and an n naught, which must be non-negative, such that Fn is always less than or equal to C times Gn. Okay, so what we are saying is Fn is bounded by Gn, or some constant multiple of Gn. It will never be greater than Cgn. Okay, so if that is the case, Fn is said to be big O of Gn. Again, like I explained before, this term is or is equal. You have to be careful about it. We are not saying really they are equal. We are just saying Fn belongs to the set. So in other words, what we are saying is big O of Gn actually is a set of all functions Fn, for which we can find those two constants, C greater than 0 and n not greater or equal to 0, for which this inequality would always be true, that Fn is less than or equal to Cgn for all n greater than n naught. Again, to simplify it even more, we are simply saying big O of Gn is a class of all functions that grow no faster than Gn. They will never be faster than Gn. They are all below Gn. Okay. Again, like we did for the big theta, let us see what we are saying graphically. That will explain it even better. So this is the graph showing the relationship between Fn and Gn in the case of big O. So here, as you can see, we are only concerned about the upper bound. So again, like we saw for the theta, before n naught, there is no guarantee that Fn is going to be less than Gn. You can see here Fn is bigger, then it went a little below, and then it became bigger again. But from n naught forward, Fn is always less or equal to Cgn. So Cgn is always going to be bigger. Okay, so if that is the case, we say that Fn is big O of Gn. Fn belongs to the class of big O of Gn. Alright, or Fn is bounded above by Gn. It can never grow faster than Gn. So all these are different ways of expressing the same thing. Alright, Fn is big O of Gn if we can find a constant c greater than 0, n not greater or equal to 0, such that for all n greater than or equal to n naught, this inequality will always be true. Fn is less than or equal to Cgn. Okay, let's take examples like we did for the theta, Big-Theta, although this time we will not take as many because I think we understand the idea. So it says show that Fn, which is equal to 10n cubed plus 5n squared plus 17, is big O of n cubed. Now if you look closely, this is exactly the same first example that we considered for the Big-Theta. We said at that time that Fn is theta of n cubed. So we are now saying it is also big O of n cubed. Okay, so to prove, if we wish, we can simply refer to our earlier proof of theta, because in that we were able to find both the two constants that satisfy both the two inequalities, and this time we are concerned with only one of the inequalities. So if we are able to satisfy both the two inequalities, it means we are able to satisfy the one inequality that is required here, okay, which is the one on the right, Fn less than or equal to C2Gn. This is the one we are looking concerned about now, not the one on the left, which is C1Gn less than or equal to Fn. We're not concerned about that. We are concerned with the right hand side. So one way of showing this is to say that it was shown earlier in example 1 that Fn is theta of n cubed, meaning Fn is bounded both above and below by n cubed. Therefore, Fn is bounded above by n cubed. Nothing to add. But maybe the one reading your answer didn't see example 1. So suppose we didn't have example 1, how do we go about it? Exactly similar, but just concentrate on the right inequality. So here I say alternatively, we do it according to the definition. We need to find two constants, c greater than 0 and n naught greater or equal to 0, such that Fn is less than or equal to Cn cubed or Cg for all n greater than n naught. And all we have to do to find the C is the same way we did to find the C2. Just upgrade these two other terms to n cubed as well. So if you do that, your function will be less than or equal to 10 plus 5 plus 17 n cubed for all n greater or equal to 1. And therefore, if we take C to be this constant value and n naught to be 1, then we will have found the two constants that we need, and so the inequality will be true for that value of C for all n greater than n naught, where n naught is equal to 1. and therefore Fn is big O of n cubed. Okay. Now, here are some other examples of functions Fn that are inside this class of big O of n cubed, just to show you how it differs from theta of n cubed. Obviously, these first three are also theta of n cubed, so there isn't much difference here. We are only ignoring the lower terms and also the coefficient of n cubed. But look at this set. N squared, we are saying, is also big O of n cubed, belong to this class. N squared over 1000, even n to power 2.9999, or n alone without any power, they all belong to big O of n cubed. Why is that so? Well, it is so because in big O, as I told you, we are concerned about the upper bound only. Definitely n squared cannot grow faster than n cubed. Similarly, n cannot grow faster than n cubed. So all these functions, they grow no faster than n cubed, and therefore they are all considered as big O of n cubed. In other words, they are bounded above by n cubed. I hope that makes sense now. Clearly, these ones are not theta of n cubed, because theta is looking at both the upper and lower, and this will not satisfy the lower bound in the case of theta. Okay, only the upper bound can be satisfied, so they are big O of n cubed, but definitely not theta of n cubed. Okay, so let's look at the other asymptotic notation, which is called big omega. So this is the asymptotic lower bound. Let Fn and Gn be non-negative functions over non-negative arguments. Then Fn is said to be big omega of Gn if there exist positive constants C strictly greater than 0 and n naught greater or equal to 0, such that Fn is greater or equal to Cgn for all n greater than n naught. So if you can notice, again, this is very similar to the theta and big O. The only thing here is, unlike big O where we were concerned about the upper bound, here we are concerned about the lower bound. You see, this can be represented as Cgn is less than or equal to Fn. So clearly this shows you that in this case we are only concerned about the left inequality. If you compare this with the theta, we were having C1Gn is less than or equal to Fn, and that is less than or equal to C2Gn. Okay, so in the big omega, we are only concerned about this left inequality. In the big O, we were concerned about this inequality. This is the idea. Alright, so like big O, we only need to find one constant which will satisfy this particular inequality. So in other words, we are saying big omega of Gn is a class of all functions Fn, where Fn is non-negative, for which there exist constants C greater than 0 and n not greater or equal to 0 such that the function fn is always greater or equal to cgn for all values of n greater than n naught. In other words, to make it even simpler, the set big omega of gn is a class of all functions fn that grow at least as gn. They grow at least as gn. This is the point. So they grow either gn or faster than gn, but not lower than gn. This is the idea. Maybe to make this even more clearer, let's look at the graph once more. This is the idea. So you can see that gn is the lower bound this time. So for the values, again, initially before n naught, the function may fluctuate. Yani fn could be even below the gn. As you can see here, it is below, then it went up, then it came below. But from this point onward, from where n is equal to n naught forward, fn is always greater. Okay, the gn times c is always below, and therefore gn is the lower bound for fn. All right, fn grows at least as gn. So gn or more, but not below. This is the idea. So this is how we define the big omega. Let's take an example. The same example that we saw for the big O and earlier on for the big theta. We're going to show that it is also big omega. Show that fn, which is equal to 10n cubed plus 5n squared plus 17 is big omega of n cubed. Proof. So again, like we did for the big O, if you wish, you can refer to example number 1, because that example shows both the inequalities. It was shown earlier in example 1 that fn is theta of n cubed. Therefore, fn is big omega of n cubed. But if we don't have example 1, how do we prove this? Well, we prove it in a similar manner. This time even much easier because we are only concerned with the left inequality. So we need to prove it from the definition. And the definition says we must find a constant c greater than 0 and n not greater or equal to 0 such that this inequality is true. Now, if we just take the 10n cubed, definitely the function will be greater or equal to that. So 10n cubed plus 5n squared plus 17 is definitely greater or equal to 10n cubed. Okay, because on the left we are adding these two terms and they are not added here on the right. So this term on the left is greater or equal to the one on the right. And this is true for all n greater or equal to 1. Therefore, if we take c to be 10 and n not to be 1, we will be able to satisfy the inequality for all n greater than n naught. Again, let's take other examples just to show you the relationship between big omega and big theta. So for the first group, there is no surprise. Any function for which we have n cubed as the highest term, to find the big omega, again, you just need to ignore the other terms and the coefficient of the n cubed. Alright, so there's no surprise here. What is surprising is here, that these functions are also big omega of n cubed. Okay, so here you see we have n to power 4. It could be n to power 10, n to power 100. All of them are actually big omega of n cubed, because this function n to power 4 is going to be greater or equal to n cubed. N to power 4 is greater or equal to n cubed. All right. So we're not only concerned about equality here. Equality usually is for the tight upper bound, which is the theta. Any function that is greater or equal to the gn will be big omega of gn. I hope that is clear. So obviously n cubed log n is greater or equal to n cubed. Even n to power 3.0001 is greater or equal to n cubed. So all of these are going to be big omega of n cubed as well, but they can never be big theta of n cubed, because big theta is about tight upper bound. Okay, so I hope this is clear. Now the relationship between the three, I think from what I have explained so far, you should be able to deduce the relationship, but we will say it explicitly here anyway. So these are our three graphs that we have already seen below. We can see that in the case of theta, Fn is bounded both above and below by some constant multiple of Gn. So they grow exactly the same rate. In the case of big O, the Fn is always less than or equal to Cgn. Whereas in the big omega, Fn is always greater or equal to Cgn. Okay, so this is the first point to note. It follows, therefore, that big theta, the set big theta, is the intersection of the set big omega and big O. All right, remember these are sets, as I tried to explain, the set of all functions. All right, so only those functions that can be considered in both big O and big omega can be said to be big theta. And because of this, we have this theorem. It says that Fn is big theta of Gn if and only if Fn is both big O of Gn and big omega of Gn. All right, if it is both, then it is said to be big theta of Gn. And the proof is just from the definition of both big omega and big O. Now, apart from the three main asymptotic notations, big theta, big omega, and big O, we also have two others. Let's start with the little o. Fn is said to be little o of Gn if for every c greater than 0, for every constant. Notice here the definition is slightly different. It's not saying there exists a constant. No, it is saying for any constant, for all constants c greater than 0, we can always find an n naught such that Fn is strictly less than Cgn for all n greater than n naught. All right, so the difference here is this is a strict inequality. Fn is strictly less than, whereas for the big O we say Fn is less than or equal to Cgn. Okay, so in other words, what we are saying is the little o of Gn is the set of all functions Fn which are non-negative, for which for any c greater than 0 or for all c greater than 0 we can always find an n naught such that the function is going to be strictly less than Cgn for all n greater than n naught. Another view of it, we can use limit. If you remember your limit from calculus, we are saying if you take the limit of the fraction Fn over Gn as n goes to infinity, you're going to get 0, because this function Gn is strictly greater than Fn. So as you increase the value of n, you are dividing this by a very big value, so eventually you will get 0. This is another way of putting it. Let's see examples. You see n to power 1.9999 is definitely strictly less than n squared. Therefore, we can say this function is little o of n squared. Okay? Yeah. Can we say n squared is little o of n squared? No. Because the inequality here has to be strict less than, not less than or equal to. Okay? So similarly here, if you take n squared and you divide it by Lg of n, Lg is log to base 2. Log to base 2 of n definitely is going to be less than n squared, and therefore it will be considered to be little o of n squared. Okay, this is the point I stressed earlier. N squared is not little o of n squared. Just like we cannot say 2 is less than 2. 2 is not less than 2. 2 is equal to 2. Right? Yeah. What about this? N squared divided by 1,000, or even divided by 1,000,000. This is not little o of n squared. Why? Because, see, this is a constant value. And normally we said we ignore constants. We are only concerned with the term with the n. So actually this is just n squared. And n squared cannot be little o of n squared. I hope this is clear. Right. Now let's look at the last one, little omega. So Fn is said to be little omega of Gn if for all c greater than 0 we can find an n naught greater or equal to 0 such that Fn is greater than Cgn for all n greater than n naught. So again, the point here is we must have strict greater than, not greater or equal to. If it's greater or equal to, then it is big omega. But if it is, if Fn is strictly greater than Cgn, then it is called little omega. Okay, so just to put it in other words, like we did with the little o, little omega of Gn is the set of all functions Fn which are non-negative, for which if you take any constant c greater than 0, you will be able to find a constant n naught for which Fn is strictly greater than Cgn for all n greater than n naught. So again, If you look at it from the limit point of view, if you take the limit of fn divided by gn, as n goes to infinity, we will have infinity. Why? Because you see, this gn is a very small function. I mean, it's smaller than fn. So remember, if you divide a value by a smaller value, by a fraction, you keep getting bigger values. So as n increases, this fraction goes to infinity. So if that is the case, then fn is said to be little o of gn. Okay? Yeah, so fn is strictly greater than gn. This is basically the point to note. These are examples. So n to power 2.0001 is considered to be little omega of n squared because it is strictly greater than. Okay? Similarly, n squared log n is definitely little omega of n squared. But n squared cannot be little omega of n squared. They are equal. So it cannot be, I mean, we didn't satisfy the strict greater than. Alright, so those are the examples. Analogy with real numbers. I like this slide very much because it tries to relate the 5 different asymptotic notations to something you already know, which are the real numbers. So let's go through it. It says intuitively, the asymptotic notations can be related to relationship between real numbers as follows. We start with the little o. So fn is little o of gn. It's best to think about it like saying a is less than b. Okay, in other words, just like a is less than b, if we say fn is little o of gn, we are saying fn is less than gn. Okay, big O. Now big O is best to think about it as a is less than or equal to b. In other words, fn is big O of gn. It's like saying fn is less than or equal to gn. Then in the middle we have theta or big theta. So the big theta is best to think about it as equality, strict equality. So fn is theta of gn. It's like saying fn is equal to gn. They grow exactly at the same rate. And then big omega. So big omega is best to think about it as greater or equal to. So fn is big omega of gn. It's like saying fn is greater or equal to gn. And finally, the little omega. Little omega is like strict greater than. A is strictly greater than b. Okay, so fn is little omega of gn. It's like saying fn is strictly greater than gn. Now if you can see how they are arranged, we start from less than. A is less than b, then a is less than or equal to b. Alright, so getting closer from less than to less than or equal to, and then to equal to. And then now it goes the other way, greater or equal to, and then finally strictly greater than. This is how to think about these 5 asymptotic notations. Let us now look at some properties of asymptotic classes. The first one is called the transitivity property. So let Fn be equal to theta of Gn, and Gn be equal to theta of another function Hn. Then it implies that Fn is actually also big theta of Hn. Yeah, so this is obvious because what we are saying is if Fn is equal to Gn and Gn is equal to Hn, remember theta is very much like saying equal. So if Fn is equal to Gn and Gn is equal to Hn, definitely Fn is equal to Hn as well. Now the transitivity property holds actually not only for theta, but for all the other notations as well. Big O, big omega, little o, and little omega. If you take big O, for example, remember the way to relate the big O, we just say less than. So if Fn is less than Gn and Gn is less than Hn, definitely Fn will be less than Hn, and so on and so forth. So this is true for all of them. Next property is the symmetry property. So here it says Fn is theta of Gn if and only if Gn is theta of Fn. Now here you have to be careful. The symmetry only applies to theta. It doesn't apply to the others. And if you think about it more closely, what we are saying is this will only hold for equality if Fn will be equal to Gn if and only if Gn is equal to Fn. You cannot say the same thing with omega, because with omega, if Fn is less than or equal to Gn, doesn't imply Gn is less than or equal to Fn. It will only hold true for the equality, so the others do not hold in the case of symmetry, only big theta. And another one is the transpose symmetry. Transpose symmetry. So the first one says Fn is big O of Gn if and only if Gn is big omega of Fn. So this is obvious again. If Fn is less than or equal to Gn, then definitely Gn is greater or equal to Fn. Okay, remember always to think about omega as greater than. Okay, now this transpose symmetry is also true in the case of little o. Okay, Fn is strictly less than Gn if and only if Gn is strictly greater than omega, little omega of Fn. Okay, yeah, so these are the ones that we use for the transpose. So you can have big O on the one side and omega on the other, or little o on one side and little omega on the other side. Now you cannot use theta for the transpose. Okay, so those are very important properties to note. We take two more general examples before we close. Asymptotic running times of polynomial. Actually, most of the examples we saw earlier were on polynomials. This example try to generalize it. Okay, so a polynomial of degree k can always be said to be big O of n to power k. Proof. So suppose your polynomial is this. Of course, polynomials are always in this form. Some constant bk times n to power k. So this is a term with the highest degree, plus some constant coefficient bk minus 1 times n to power k minus 1, and so on until we reach b1n and b0. Where the bk, the term with the highest degree, is not 0. The others could be 0, but this one must not be 0. Otherwise, the highest degree of the polynomial is not k then. It will be the first bigger one that is not 0. So suppose we have that. Then we can, in case some of these coefficients, bk minus 1 and so on, in case they are negative, let us take their absolute value. So we are sure that the terms are all positive. Then we can say our function fn will be less than or equal to the resulting polynomial, where we use the positive coefficient rather than negative. So this is obviously true, because if ai is the absolute value of bj, then some of this may be negative, and therefore the result when you add them all will be less than if all of them are positive. So with that in mind, suppose now we replace all the other terms, n to power k minus 1, n to power k minus 2. Suppose we replace them with n to power k. Obviously, we will have an expression that is even bigger than what we have here, right? Good. So that's what we are saying here. If we do that, then what we have will be less than or equal to n to power k times the summation of just the constants. This is similar to what we were doing actually with those simple examples. We just upgrade each of those other terms to have the highest degree of n, so that we only need to add the coefficients. Okay, so our function will be less than n to power k times the summation of the coefficients. Well, summation of constant is a constant, so we can call it c, and it will be, the result will be c times n to power k. And clearly then we can take that c to be the c that is required by the definition of big O, and we will be able to satisfy the inequality that fn is less than cgn. Okay, remember our gn is n to power k. So this is the idea. We are just saying that actually any polynomial can be considered as being in the same class as just the term with the highest degree. Okay, so you can clearly see that from this. The examples we saw earlier are just specific examples of this general one. Yeah, so this is the point. Now let's go back to our insertion sort, which we saw in the last lecture. If you remember, we found a function, the running time function, to be a polynomial of degree 2. So now we are going to prove it formally, that insertion sort is big O of n squared. Okay, proof. So the running time was a function of n squared. So let us put it like a quadratic equation, an squared plus bn plus c. if any of A, B, and C are less than 0, replace the constant with its absolute value. Okay, yeah. So in that case, we can say that an square plus bn plus c will be less than or equal to an square plus bn square plus cn square. In other words, we can upgrade these two terms to also have a degree of 2. And clearly, we can factor out the n square, so we are left with just the coefficients, which will add to one constant. So if you let that constant to be c prime to be equal to a plus b plus c, and we let n naught to be equal to 1, then our proof is complete. So clearly, insertion sort is big O of n square. Question: is insertion sort big O of n cubed? I hope you can answer this question. Obviously, yes. Insertion sort is also big O of n cubed. Remember the big O, we're just trying to find the upper bound. So insertion sort is n square, and n square is definitely less than or equal to n cubed. Okay, so insertion sort can be considered as big O of n cubed. It can be considered as big O of n to the power 4, and so on. Okay, this is why big O only gives you an upper bound. It says your function cannot perform worse than this. It doesn't give you a tight bound. Yeah, so only theta can give you that. And in fact, insertion sort is theta of n square, not only big O of n square. In fact, it's theta of n square. So this is true. But can we say insertion sort is big O of n? Definitely not. N square cannot be less than or equal to n. Okay, always remember when we say big O, think of it like less than or equal. Can we say n square, which is our function for the big O, for the insertion sort? Can we say it is less than or equal to n? No. So this is definitely not. Alright. Okay, we're gonna conclude this lecture by trying to compare these complexity classes so that we have an idea of which of them is growing faster than the other. How do they relate, the different complexity classes? So it says here comparison of some common functions as n increases. So these are the common ones that you will normally see when you analyze algorithms. You could end up with n log n, n log n, n squared, n cubed, or exponential 2 to the power n. Alright, so these functions are shown in this graph as n increases. Now, so the purple one here is the n cubed. It looks like it is big. And so on. The brown here is the exponential. So notice this is very interesting actually, and that is why the n naught is very important in the definition of this asymptotic notation, because you may not be able to see the relationship for small values of n. Only when you reach a certain value of n, the relationship will be clear to you. See, at this point in time, n cubed seems to be growing faster than exponential 2 to the power n. Okay, for example, for n equal to 3, obviously n cubed will be 27. okay, but 2 to the power 3 is only 8, so 27 is bigger than 8. All right, but let's see what happens as you increase the value of n. Yeah, so this is showing. Let's go even the next slide. I think it will show it better. Yeah, so now if you take, for example, n to be about 10, then you will see that the two functions, exponential and the n cubed, they are almost the same when n is about 10 actually. Okay, and we can see why that is so, because 10 to the power 3 is like 1000. 10 to the power 3 is 1000. But also 2 to the power 10 is like 1 kilo, so 1024. So they are about the same when n is equal to 10. Okay, so n cubed started to be faster, but now the exponential has caught it at about n equal to 10. Now increase the values of n and c. Even for n equal to 15, for example, or around 20, you can see that the exponential now is really going much faster. The brown here is the exponential than n cubed. Okay, so the point is this relationship or these different classes, don't be surprised that one of them is growing slower initially, but as you increase the value of n, it outgrows the others. Okay, particularly the exponential function actually is the most expensive. It grows higher than any other function. Okay, then the rest will go accordingly. So n cubed, among at least the ones we have here, n cubed will be the next one, and then n square, then n log n, and then log n, and then n. And there's another one we didn't show, which is a constant. So the constant is the slowest one because it remains constant. It doesn't grow actually, it is fixed. Okay, yeah, so this are the relationship. So in terms of algorithms, if your algorithm happen to be having a running time of exponential, then you are in trouble. It is very, very slow because these values are the cost of running the function. Okay, so the cost obviously is much more in exponential compared to other polynomials. Okay, and then it keep coming down. So the best function you can have, or the best algorithm you can have, actually is the constant one. It's independent of the input. Okay, then the one like log n. Okay, then n log n, and so on and so forth. This is the idea. Yeah. The last slide here is showing you some exercises. All of them are from the book. Let's go through them. Say let fn and gn be asymptotically non-negative functions. Using the basic definition of Big-Theta, prove that the maximum of fn and gn is equal to the theta of fn and gn. Okay, show that for any real constants a and b, where b is greater than 0, n plus a to the power b is actually theta of n to the power b. So the constant here doesn't change the theta. It is still just theta of n to the power b. Explain why the statement the running time of algorithm A is at least big O of n squared is meaningless. This statement doesn't make sense at all. Okay, explain why. And the last one is 2 to the power n plus 1, big O of 2 to the power n, and also is 2 to the power 2n the same as big O of 2 to the power n? Think about this. All right, so that brings us to the end of this lecture. Thank you very much.